Connect seminar of the season. My name is Michelle Melendez. And well, I'm just gonna start mentioning you about the purpose of this series of EPSP Connects. So the main reason of those Connect seminars is to bring the community together and to help establish connections between people who might not be able to interact with others in a different setting. So we're very happy to have you here. I would like also to thank all the EPSP Connect team members who helped plan and organize the series, who reach out to potential speakers and coordinate with them, and who advertise in social media and make sure that the series information is up to date on the website. So joining me today as a co-host is Shashank, who will help us with a Q&A session at the end. Shashank, what's the plan?
Hi, everyone. Thanks, Michelle. This is Shashank. So please post your questions in the chat as you see the slides, and Michelle and I will monitor them. If you prefer, in the end, we can also unmute you and you can ask your questions directly. And I'm assuming there are some people who are listening to our live stream on YouTube. So we'll keep also an eye for it, like for the questions on there as well. Yeah, that's the plan.
Thank you very much, Shashank. So now, finally, our speaker today is Dr. Evan Dethier from Occidental College, and I'm very happy to host him. So Dr. Dethier is an assistant professor in this Occidental College in Los Angeles, California. He's a geomorphologist and hydrologist using satellite and on-the-ground measurements to understand how river systems respond to major changes, both anthropogenic and natural. Dr. Dethier, please take it away.
Thanks for the introduction and the invite. It's great to be here talking with people today, and I hope that what I talk about hopefully inspires you to ask questions or maybe even join in collaboration on this work. I think it's pretty important and not enough attention is being paid yet, so certainly reach out to me. I'm at Occidental College, so you can find me on that website or email me. My email is Dethier, just my last name, at oxy.edu. And that's on the last slide as well. So I'm really happy to be here today to talk about work that I've been doing for quite some time now, looking at the effects of mining, particularly mining in and just adjacent to rivers across the world. And this is part of a collaboration funded by NASA and the National Science Foundation with my colleagues at Dartmouth, at Wake Forest University and Cincia, colleagues in Peru, and then also undergraduates who have worked with me throughout the project, both at Dartmouth and Bowdoin College, and actually now at Occidental as well. So thanks in advance before I start to all of them. The sort of central motivating questions here for my work are how do we make sense of the changes that humans are visiting upon the Earth, particularly as they interface with the natural system and the changes that happen just due to natural events, floods, droughts, and that sort of thing. And I mostly focus on rivers, and rivers are a threatened resource these days. Across the world, there are changes to rivers that are in many ways unprecedented, at least in their scale and scope, even if they're similar in many ways to things that humans have been doing in rivers for millennia, if not longer. And especially recently, there's been this large rise in mining, some related to the clean energy boom, though mostly probably just related to normal cosmetic extraction for gold and silver and that sort of thing in rivers, the same way that in the 1850s and 1870s in the United States and Canada, there were mining booms. Those are happening now across the global tropics. And as these mining footprints expand, really the question is, can we improve environmental outcomes? Because mining is almost never a positive on the environment, but it would be great if we were able to figure out ways in which mining activity was not the negative or the strong negative that sometimes it is. To improve environmental outcomes, though, first we need to know a lot more about these mining activities and the environmental effects that they have on these river systems, these important river systems. And so the first question here really is, can we document the environmental outcomes in these rivers that are affected by mining? And this is a many years long project that began not looking at mining specifically, but really just looking at how rivers and their variable sediment transport lead to different signatures that we might be able to observe, either with our own eye as different colors that we see in the rivers that we pass by or swim in or drive next to or fly over, or as they appear to satellite images or satellites, which can record information that's beyond what we can see with our eye into different parts of the spectrum that might give us a little bit more of an insight. And so for years now, I've been looking at these satellite images, and so have many other people, trying to get a better handle on just how these differences in suspended sediment concentration or mineralogy or chemistry manifest as different spectral signatures to satellites. And what we can see here is some part of that work showing each one of these major rivers in the world and their seasonal or monthly signature in terms of what they would look like to the naked eye in some ways or to the satellite. So at the top of each one of these little wheels is January. And as we progress around the wheel or around the pie, each pie slice or each wedge of the wheel is showing 1 month in that month's river color in true color, so red, green, and blue combined. And then each one of these pie slices is scaled by the normalized river discharge. And so what we can see is the strong seasonality in some monsoonal climates, with major differences both in discharge and suspended sediment concentration versus some more, let's not say boring, but muted changes that we might see in some of these more temperate environments. So we can look at these differences in a qualitative sense like we are here, but what's really valuable, at least in my mind, is trying to extend these qualitative observations to thinking more quantitatively and trying to train our satellites or train our computers to interpret these satellite images and make some sense of the information that they're delivering to us and maybe put a number to it. And fortunately, to some extent, that's possible. So if we look here at a different monthly time series, in this case, the Green River, tributary to the Colorado River in the United States, and again, looking across from January to December through a year, each one of these images shows actually a monthly composite compiled over many years. So the average pixel value for many years worth of data, but shown at the same location in each image. And what's really nice here is that we can collect the Landsat data. In this case, the Landsat satellite is what we're using for the most part. And then identify river water pixels at a place where the USGS or other agencies or other scientists have taken actual measurements of suspended sediment concentration in the river. And so we can take these qualitative observations that we're looking at in the satellite and then match them to actual on-the-ground measurements of sediment concentration. And when we join them together here at the Green River in Utah, we can see the suspended sediment concentration does vary sort of predictably with the color changes that we see in the river. And we can do that for a single river. And honestly, it works best when you do. But sometimes you don't have in situ data for the rivers that you're interested in. And so what we've tried to do is build a large set of algorithms that essentially looks across all of the different stations where we make these measurements and across all of the different satellite images of those stations taken at the same time as the in situ measurements are taken, and then make a larger relationship that we hope is applicable to rivers where we don't have many measurements or we don't have measurements at all. So what we've done here is compiled a large data set. It's 130,000 odd images with paired measurements from on the ground. And then what we're able to do is then tune that larger calibration or set of calibrations to look more locally if we have a more specific approach. So for example, here we're testing it on independent data from Brazil, from the Rio Madeira there, in an area that we're quite interested in, just to see if it works well. And it doesn't work perfectly by any means, but no measurement of suspended sediment is perfect. And we're trying to better understand rivers where there really isn't much on the ground measurement. And so we don't let the perfect be the enemy of the good here, and try to acknowledge as much as we can the areas where we fail or don't capture all the variation that might exist. And then forge on with as much of a sense of how these rivers are operating as possible. And we think that the results are quite robust, but we're also always reliant and hopeful that people are going to continue to make these in situ measurements because they serve as both a great training data set, but also a great test and check on the satellite measurements. So I'll talk more about that just a little bit at the end. The problem with the global approach or global algorithm is that, as we saw before, rivers look quite different in different parts of the world, or even different parts of a continent or a country, or even adjacent rivers might have quite a different spectral signature for the same amount of suspended sediment. And so here I'm showing 6 different groups that we automated to create separate, not quite bespoke, but general algorithms for river groupings where the spectral signature of those rivers is quite similar to one another. And so you can see that some of these rivers might be a little bit grayer, some of them might be greener, or some of them might be more yellow. And as a result, we sort of automatically deploy the algorithm to that particular river or set of rivers. So we have 6 of these. And 6 we chose just based on optimizing these relationships. But if you chose 7 or 8, the results wouldn't change much. If you chose 5, it would be a little bit worse. And as you go towards like 4, 3, or 2 algorithms applied to the globe, you really actually do miss a lot of the variation in certain river types that just don't quite resemble the other ones that are a little bit more dominant on Earth. Again, this is a project that we're continuing to try to develop and expand new satellite types. But in essence, it allows us to look across these different river types and with some reasonable amount of confidence, predict the suspended sediment concentration, not just for the days where we have in situ measurements or the places where we have those measurements, but for all of the days and all of the river reaches where we do not. And so that allows us to essentially jump in our time machine and go back to the early or mid 1980s when the Landsat program, at least the Landsat 5 program, began, and then run all the way forward to the 2020s now as Landsat continues to collect data that's totally valuable and valid across the entire globe. So the sampling resolution here is sort of in a best case scenario every 8 days in places where the Landsat satellite overlaps with itself, the paths overlap. More often it's 16 days, and 16 days is best case because there's often clouds or snow and ice that covers the river and makes it not visible to the satellites. But still, we're able to look across this long period and construct time series with thousands of measurements across thousands of rivers across the globe. And it's quite powerful, and we're hoping, again, to collaborate with as many of you as possible, trying to think about the different questions or problems that you have in all of these different arenas, where how much material sediment or how much material rivers are transporting has a bearing on the questions that you might pose. And then we have our own questions ourselves that we're trying to answer as well. What's really nice is that we're able to kind of come up with both a retrospective and a continually updating picture of the present state of rivers. So looking at rivers through the past, but also looking at them really much, right up to the present. These images come through every day, and we're able to respond in real time to flood events or other anthropogenic changes that might happen on quite a short-term and current basis. So it's it's a nice tool that now we're able to look to many different rivers and think about how they're changing. One more step here is to try to combine our estimates of suspended sediment with discharge. Again, like discharge measurements across the world are not perfect and not uniform, but where they're okay, we're able to compute suspended sediment flux, which for some applications is more valuable than suspended sediment concentration. And this allows us to evaluate seasonal patterns or longitudinal trends over time. And so what we can see here is the Danube River in Europe looking relatively consistent compared to the Yangtze River in China, which through various dam building programs and also soil conservation efforts in China has really declined its sediment flux in the last several decades. From a zoomed out perspective, what we can see is across the Northern Hemisphere, there's quite a strong decline overall, even more recently after the major dam building period in the mid-20th century. And we can see that this is especially concentrated in Europe and Eurasia, where dams have continued to be built since the 1980s, and then also in China especially. And these really do coincide with this continued wave of dam building that just hasn't been the case in other places in Western Europe and North America. However, southern rivers, especially south of the 20 degrees north latitude, for now are not thoroughly dammed. And so we can see here, compared to the percent of the annual discharge here, the amount of dam capacity is quite low compared to some of these other continents that we've been looking at. And so this metric is essentially taking all of the river flow, all of the discharge for a landmass and adding it up, and then adding up the volumetric reservoir capacity built on that continent and comparing them. So it's just a fraction for each year. So for the Colorado River, for example, the actual percent or the reservoir capacity would be greater than the annual flow, at least if the reservoirs are empty. In other places, it's not that way, but the preponderance of dams in a certain area can mean that there's 40 or 50% in the entire landmass can be held back on a given year at full capacity. So South America and Oceania really are bucking this global trend towards dam building for now. And this corresponds also with what we see for changes in suspended sediment flux relative to the pre-dam condition, with South America and Oceania really as outliers, as at or above, in some cases, the pre-dam estimated flux for these rivers, as opposed to the rest of the land masses, which really have fallen quite a lot below that pre-dam line. What we can see here, focusing in from a hemispheric perspective, is that there's this major north-south divergence in suspended sediment flux trajectory. And in many cases, this isn't just a neutral, flat sort of maintenance of previous, like pre 1950 or 1980 suspended sediment flux. It's actually quite a pronounced increase across especially this band around the equator, from sort of like plus 20 degrees north to 20 degrees south. And so in our more recent work, and what I'll especially focus on today here, is trying to think about the different factors that have conspired together to cause this increase in suspended sediment flux or concentration in this subset of rivers. This analysis that I'm displaying here was really just for the outlets of rivers around the globe. What we did subsequent to this is look into the watersheds, farther up the watersheds for these particular rivers, and just see of the rivers where there was an increase in suspended sediment concentration, whether or not there was acute erosional land use change in those systems. And for the most part, like more than 80% did have this type of land use change that really we could identify as being an increase in erosion with a connection to the river. What does that look like? Well, it's a combination of things. Deforestation basically is everywhere, but close behind is alluvial gold mining, the effect that I'm going to focus on today, as well as sand mining, oil palm cultivation, and then other non-agriculture or non-oil palm agriculture. And we can see just how these different operations carried out by humans change the landscape with an erosional effect, looking at deforestation, alluvial mining, sand mining, oil palm, with it, especially the clearance phase of these operations, and then other agricultural effects like grazing or accentuated runoff and that sort of thing. What's really sort of interesting to me here is the alluvial gold mining of these, I think, has reached or has received the least amount of attention. And so I wanted to follow up on this, and we have been for several years now. But I don't think that it's well known, the processes that are involved in this type of mining in rivers. And so I wanted to begin by just giving a sense of what this looks like in the rivers themselves. The process begins in general with deforestation, because the whole theory here is that instead of mining hard rock out of the mountains, you let the forces of water and gravity and time do that mining for you, and then transport the gold downstream or other minerals downstream, where then it's deposited in loose sediments. But generally, especially in these tropical areas, the sediments then are covered by tropical jungle, or they're covered by rivers. And so the first step here is deforestation. Then there's quite an involved sediment excavation and sluicing process that involves the digging of pits, the pumping of water and sediment through sluices, followed by, in many cases, a step where mercury is added, in this case, to this bucket, which is being stomped, sort of like grapes turning to wine. And then the gold forms an amalgam with the mercury that then can be kind of fished out of the bottom of these barrels and then burned off either right there on the riverbank or on the river itself, or in like a gold shop in a nearby town where this is happening more at scale. Pretty much at the end of that process, everything else is just either left or in sort of like timeless fashion discharged back to the river, which then transports it downstream with varying degrees of effectiveness. And so what we can see here in this video that I took a couple summers ago is the gold mining sort of like signature along this river, the Madre de Dios River in Peru, where there's in-channel mining happening. Each one of these piles is a set of sediment that's been gone through, and each one of these stakes on top says essentially it's been gone through once. People might go through it again subsequently to kind of like do a second pass and then go from there. So it's quite a major effect. This excavation happens right in the rivers themselves or right adjacent to them, with potentially major consequences for miners, of course, themselves, who have the greatest exposure, but then also for downstream water quality, fishing, bathing, drinking water, recreation, tourism. Like, these rivers are really important. Lots of people use them, live on them, move up and down on them, recreate on them. And then we'll talk a little bit just briefly about desertification and water retention, which also seems like it may be a casualty of this process. In the mining areas themselves, they can be quite extensive and extend much past the actual river channel. So here's just driving through the jungle, and as we're going, we can see this is my little like where I am Google dot, and passing through this large swath of jungle on the way to then what opens up into sort of an incomprehensible expanse of essentially like a beach environment that stretches for at least 1 kilometer across and many kilometers up and downstream in this large band. It's pretty hard to really give a sense of scale here, but this is a mining operation in a place called La Pampa in Peru. It's actually, there's been an intervention against mining in this area. So when we were there was no mining, though there's some encroachment back into these areas where mining is technically illegal, but has been going on for many years. And what we can see here is, some of the people who are thinking about these questions, biologists who live in the area and are thinking about rehabilitation and revegetation of these now sort of heavily disturbed or perturbed landscapes, and how to restore vegetation in a place where it's actually quite hard to grow because much of the topsoil and the fine sediment has been transported out of the system by the streams or through the sluicing process. And now there's just not a whole lot of shade, not a whole lot of soil nutrients, and it's a tough job. In addition to the deforestation, of course, there's just this comprehensively changed hydroscape. So what we see is instead of a single threaded river running through the forest that would have been essentially imperceptible from satellite imagery, now we see a wide band with mining pits and certainly not single threaded stream running basically just opportunistically from pit to pit, depending on where the easiest path is, or when things are active, where miners are diverting it to provide like the best flow to their system. So in the pre-mining world, certainly these rivers were dynamic. I don't want to give the sense that they were just stable and in stasis. But after mining, there's quite a pronounced effect with these plumes of sediment coming from mining areas, which might be here or here, and certainly along and in the channel as well, with a seriously elevated suspended sediment signal. So in 2018 and 2019, we worked to try to think about the scope of this problem or these changes in some of these watersheds in Peru that had received quite a lot of attention for the biological side, but not much attention on the sort of hydrology and geomorphology. And what we saw was not much of a surprise, but quite a pronounced change from before mining, showed on the left side of each one of these dashed lines, to after mining started in each one of these river systems in the Madre de Dios watershed. And so it's a stepwise change in many cases, with then a continued increase after that initial mining begins. And there's many things that might account for changes in suspended sediment concentration in these areas. Certainly the intensification of the hydrological cycle has been identified as a potential driver or accentuator. But when we look at rivers that are up in the preserves nearby, there's probably a statistically significant increase, maybe due to some of those factors, but certainly nothing on the scale of the changes to suspended sediment concentration that we see in these rivers that are affected by direct mining. So it's a large problem or a large challenge with a large footprint in Peru. What I think we didn't realize at the time was just the scope of this worldwide. And the last several years, we've been trying to wrap our arms around, just that scope or the scale of mining globally. And what we see here is that this increase in tropical river sediment flux is truly a global phenomenon with a global footprint. And what we are showing here, all the different mining districts. So these aren't just like individual mining pits or sites. These are large districts where there's multiple mining operations happening across the globe. And you can see that they're really concentrated with quite few exceptions in the tropics. The way we're defining these districts is major mining operations that happen in the channel or in riparian areas with a direct connection to the channel, direct surface water connection. So we're not looking as much at sort of self-contained, at least to some extent, pit mines, but rather at mines that happen in strips or pits like along the river or in the floodplain, or sometimes in terraces and adjacent tributaries. And what we can also see is that this is especially mining for gold. So although much has been made recently of the the tie to critical minerals and the the energy transition. So far, at least, though those are contributing to this global challenge, gold, primarily for cosmetic purposes, is the single largest driver by a long shot. More than 80% of these sites, there's mining for gold, even if there's also some mining for other minerals. Other major players are diamond, particularly in certain places in Africa, Angola, the DRC, Sierra Leone, and then also nickel, especially in places in Indonesia, Malaysia, and like New Caledonia down here, which has been a nickel hub for a long time. And then again, there are a few others, particularly in the eastern DRC, where mining for coltan and that sort of thing has become a major issue, and certainly something that we're working on and thinking about quite hard. And so I think when we look at this scope, first, it's sort of awe-inspiring or jaw-dropping, because these are not small operations. This is happening on a large scale in many of these places. But it's also important to think about how these are also tied directly or intimately to the communities where mining is occurring, where people are working in these mining areas. They're making their livelihood. Their social structures are arranged around there being mining operations here. And so certainly it's not just an environmental issue. It's also in many ways a human and equity issue. And so I think that as we think forward to how to address some of the challenges, the environmental challenges that are associated with mining, it's important to keep those hundreds of millions of people who are involved either directly or adjacent to this industry at the forefront of the mind. What we mostly see in the limited environmental reports that come out of these different mining areas is both the negative human and the negative environmental cost, and certainly those are real and profound, and mostly the topic of what I'm going to be covering today. And these span sort of like the individual operators who are working either alone or in small little consortiums in various of these different places, but also involve like very large corporation-backed pit mines that have very similar environmental footprints and signatures, discharge sediment and other contaminants to rivers. And we grouped kind of all of these together, didn't make much of a distinction in this initial study. So again, this is something that warrants follow-up. What we don't see so much are kind of like the view or the images of why people might choose this livelihood. And certainly there's good reasons to do it. You get to be outside, you get to be working in these rivers where many of us also like to do work and do field work. You work with your hands, tangible output, immediate gratification in terms of selling and making a profit. In many ways, though it can be a brutal life, and in some cases happens, in very bad human rights conditions. There's other operations where certainly the benefits to the livelihood and to people's well-being are quite tangible, with people posting on social media, just celebrating what they're up to, showing different parts of the process. Like here we see some sluicing happening in away from the mine in Ghana, and then the very clear economic benefits as these guys drive back to the city with literally bricks of cash that they've made from mining. So I think it's pretty important to think about these motivators or these positives that the miners and their communities feel when we're thinking about environmental concerns, or when we're thinking about intervention, especially because it's certainly not easy to intervene against operations where people are celebrating their work, making a bunch of money in places where it's often quite hard to make a lot of money, and also are able to quite easily evade the authorities. And so here we can see more mining operations. In this case, on the left video, what happens when the miners get word that there's going to be some sort of intervention against mining. The expensive part of the rig is the big engines that drive these pumping operations. But the miners just, they just dump them into the water and hiding them in, just one of many mining pits. And then they go essentially and hide in the forest while the interventions come in and dynamite their mostly relatively cheap and easily constructed wooden superstructures. And then they outweight the interventions in many cases and return. So it's certainly not like an easily solved challenge. It's one that has quite deep economic and social and political roots and ramifications, and is something that I think hopefully as more attention is paid, is not treated lightly, but also isn't sort of like treated as something where there's a quick solution or a panacea. It's something that I think needs to have quite a lot of careful thought contributed to it. Part of the challenge here is just the recent acceleration of mining. So what we're documenting here is 400 or more major operations that are occurring across the entire globe, at least 49 nations with major mining operations occurring that are discharging sediment and likely contaminants to rivers. And what we can see here is just like the tail off here is likely mostly reflective of just lack of recent imagery or challenges with like early detection of mining, because when the mining operations like initially start out, they can be a little bit hard to pick up. So I don't think that there's actually been a real tailing off in recent sort of like the last few years. I think that this is continuing to be a robust place where people are moving. And what we can see is like the signature is quite similar across the globe. So in Peru, where we've looked at some images already, in Ghana, where we saw as well those miners in the pits with the pumps and the hoses, but then also in the Democratic Republic of the Congo and in Myanmar here, all different parts of the world, very similar pit pump, sluicing operations that are occurring. And in some cases, these are really recent. In other cases, mining has been occurring for quite a long time, and operations just continue to expand their footprint. So in Myanmar here, we're looking at the expansion from mostly agriculture happening along these rivers and on the floodplains to mining completely taking over. And we can see the changes in suspended sediment concentration, which is really the piece of this that we're analyzing over that same period. So looking at a beginning sediment concentration that's essentially reflective of clear rivers all the way up to extremely turbid rivers with enough sediment flux that they can make a meaningful contribution to the large river that the tributary runs into just downstream here. And this is just one of many examples showing just the changes over time. Overall, there's just a uniform signature of the mining operations in the rivers as well. So the mining operations look similar, they use similar techniques, and they have quite similar effects in the rivers with an increase in suspended sediment concentration essentially across the board. Even in rivers that have high pre-mining suspended sediment concentration, it's still detectable. And in some cases, we can see that there's an inversion of typical seasonal cycles. That's certainly the case in Peru, where it's just a bit easier to mine during the dry season. And because it's easier to move heavy machinery, it's easier to be out there, it's more pleasant to be out there. And that's something that we've also seen elsewhere as well, with potential effects for the ecology and that sort of thing that lives in the river and might have seasonal cues. That just may be kind of like an additional consideration here. And then again, just the vastness, as we've looked at mostly zoomed in images here. Now we start zooming out and just see the extent of these mining operations, which stretch for many, many kilometers in the rivers themselves, and then on either side of the rivers into the floodplains, and in some cases up the tributaries. And just to kind of like bring it back to South America, where we began, I'm not looking at Peru here, but looking at Venezuela and Brazil. And of course, there's major mining operations in other countries in South America, including Ecuador, Colombia, many, many others that I'll show here. Overall, this is quite a serious effect, not limited to the rivers that I've shown you so far. We looked at 170 some rivers that have quite long lengths, not just very small rivers. Each one of these is greater than 50 or 60 meters wide. And what we can see here are the total river length in these countries of rivers that are that wide. And that's shown in the white bar. And then in the orange bar, we're seeing the percent that are affected by mining, where suspended sediment concentrations are elevated over the pre-mining condition or reference condition. And note here that Brazil is on a different scale than the other countries here, just because of the immense scope and river length affected in that country. But in other countries as well, we're looking at between 20 and 40 or even higher than 40% of the river's length is affected by mining. So in some cases, nearly half of a country's large river length has high sediment concentrations due to mining operations flowing the sediment into those rivers. If we look at the continent breakdown, 50% of the river reaches that we looked at have more than 2 times the pre-mining suspended sediment concentration. So that's highlighted down here with 21,000 kilometers total being affected by mining to the extent that they have double the pre-mining suspended sediment concentration, give or take, with 33 rivers overall having more than 10 times the pre-mining suspended sediment concentration. So going from a completely clear river or a mostly clear river for most of the year to one that has a lot of mud being transported through it for the entire year. And so this, again, I think shows the pressing need for policy, but also for scientific study, as the questions here that can be tackled span geomorphology, hydrology for sure, ecology or biology, and then also contaminant fate and transport, so geochemistry. I think there's a lot of scientists who have a lot to contribute here, and there's really interesting questions that can be posed, particularly related to experimental design with the amount of sediment that's being transported here and the stepwise changes that we're seeing, thinking about changes in suspended sediment transport, or recovery certainly is another avenue that I think that there could be quite a lot of study of these systems. We talked mostly about the suspended sediment concentrations, so the passage of sediment through these rivers. But I also want to just highlight a few of the geomorphic effects. These are more on the sort of like the preliminary end of what we've looked at. But we do see a strong, I would say, possibility that rates of avulsion may be increased, with several examples across the world. This one in the DRC is the most pronounced, with a major avulsion on like a sizable river downstream of mining operations, where I'm pretty sure just the amount of sediment that was building up here in this meander bend caused the river to jump its banks during a flood in 2017, late 2017. So again, something I think warranting study, and related to study theoretical work done by various geomorphologists in the past, and something that I think, especially as people consider changes in meander rates, this is something that could be highlighted as well. On a more local scale, the geomorphic effects are also quite serious and I think warrant investigation, and probably also have an effect on the ecology in these river systems. The plumes of sediment that extend quite far downstream are mostly on rivers where they're wide enough to measure by Landsat satellite, so at least 50 or 60 meters wide. But there's all this mining that's happening on smaller streams as well, where we can't really map the suspended sediment concentration effects. But likely the geomorphic changes are greatest in these streams, where there's direct excavation of a high percentage of the stream surface area into the stream floodplain or riparian area, and likely also because there's been no dilution from unmined tributaries, the highest suspended sediment concentration, which is really tough for fish and other ecology or flora and fauna that might occupy these rivers, but also might have a signal that's detectable or measurable from a more like geomorphic standpoint. And we tried to get a handle on just like the scale of this without investigating really the mechanisms or the actual effects of the changes to geomorphology. But in many cases, like entire tributary networks are excavated during these mining operations. So we're looking here in Indonesia at quite an extensive mining operation along a river where there's both oil palm cultivation down here in the southwest quadrant, and then also a whole swath of mining operations, both in the tributaries and then along the main stem as well. And what we wanted to do is really try to get a better sense of how this was going to change kind of like our top line numbers of how many stream kilometers were affected. And what we found is that when we add up all these mapped mining areas that are not on the main channel, we potentially like almost double the total number of stream kilometers that are affected. And again, we really think that these may be the ones with the most acute geomorphic changes, again, that I think are worth studying. And then finally, just to kind of like bring it back to the local, these have really tangible effects like in communities where people live or are, just living different lives unrelated to mining. Maybe it's an agricultural area, maybe it's just a place where there's industry or towns. And you can see that as these mining operations expand over time, they really subsume the stream networks that are there, and also encroach in many cases with sort of like the permission of the farmers, but in some cases without permission of the farmers, encroach on agricultural land as well. So really like a changing both of the geomorphology and the hydrology, but also like changes in livelihoods in these areas as well, with widened or obliterated channels across the riparian zone, and mining up in the floodplains and terraces, in some cases cultivated terraces, and then also tributaries. And again, just to like point to the other areas that warrant study here, there's major soil carbon nutrient disruption in these areas and fluxes to streams that are totally unquantified as yet, in addition to the contaminant fluxes, which have been measured in some places, but certainly not pervasively, and I think really warrant further study as well. And then something that I haven't touched on at all because it's much harder to measure from satellites, but really is important as part of this larger picture, is the geomorphic effect from coarse sediment inputs, which in many of these cases might be the dominant input from these mining operations, with huge deltas being built out here from nickel mines in New Caledonia into a stream that's really having trouble keeping up with those inputs. I mean, this is something that we observe like all across the world as well. So overall, it's quite a bleak picture of these threatened rivers, with almost all the large rivers going from a low suspended sediment concentration relative to what they've got now, even if absolute measurements of suspended sediment concentration were high to begin with. Now they're just higher. So this is just looking at a departure from the mean. Basically, it's a Z-score computed over time for all 173 rivers that we're including in our larger analysis. But there's, again, many additional streams were altered where geomorphic effects were probably most acute. I do want to sort of like pivot here at the end, though, to thinking a little bit about recovery, because I think not only do we need to kind of like keep a optimism as we do this work, but also this is maybe the most important work that needs to be done right now. And so here I'll just highlight in Brazil and then also in parts of Colombia, places where there was a lot of mining in the 90s and then a pause in mining in the late 90s and 2000s. And so when we look at the rivers themselves, we can see mining operations in 1992 here in Brazil, followed by a period where mining was banned in this reserve. And you can see that there was some revegetation in these mining areas that didn't shut off the suspended sediment flux to the rivers, but certainly diminished the fluxes. And the revegetation is certainly not complete, but it's incipient in this case, and does point to like the possibility for rehabilitation in these different areas. And what we can see here is that the suspended sediment concentration shown here is like Z-score. So here's the mean. That also declined from quite a pronounced high back towards like something close to the mean in not so long, in like a decade's time or less after that peak. Unfortunately, and like this points to the need for sustained policy here as well, is that in the 2010s and 2010s, mining accelerated again as those protections for this area were lifted or at least relaxed in their enforcement. And mining actually has a larger footprint than before with a comparable sediment concentration signature. So again, these are tough challenges and they don't go away easily, and it sort of like requires a sustained effort to keep them environmentally conscious or responsible. Fortunately, we have a lot of partners in this and hoping to recruit more, and that's part of giving this talk, is to try to think about these potential best practices for mining and rehabilitation. So multidisciplinary efforts are really needed here. And I want to point to the fact that we can do some of this mining with a limited footprint relative to what we're looking at here, with some relatively simple best practices. So here's in New Zealand, a mining operation that really has, in some ways, a signature from the aerial images that's similar to what we've seen in these other landscapes. And then just over a couple of years, we can see as the mining operation was shuttered, there was a plan for rehabilitation from the outset. And it basically goes right back under pasture land in the sort of couple years following. And this came from having a plan for rehabilitation that included not using mercury or other heavy metals on site to the greatest extent possible, certainly no mercury, preserving topsoil and fine sediment during the initial excavation process, so it could be like spread back over the landscape once mining ended, and then also as much as possible limiting the surface water connection from the mining operation to the stream. So certainly New Zealand's not a perfect example. There's plenty of operations in New Zealand and all these other countries where mining operations are not good and have similar environmental effects to what we've seen elsewhere. But this is, I think, a possible light at the end of the tunnel, or something to strive for, and something to try to recreate across the world. So wrapping up here, coming back to our original question, as mining footprints expand, can we improve environmental outcomes? I would say yes, but certainly not without quite a lot of effort. This really requires concerted monitoring and rehabilitation efforts. And I think that as a scientific community, it's certainly something that we should contribute to. These decisions shouldn't be made in a science vacuum. They should be science informed. And in order to do that, we need to do the science that can inform it. So I'm hoping that people will think about these issues, think about these settings, and realize that their expertise can really contribute to efforts towards, these better environmental outcomes that can be, at least to some extent, implemented in places where this might occur. So certainly reach out, and thanks for listening. I'll certainly take any questions about my work or whatever else. I appreciate everyone sticking around. Thanks.
Thank you, Dr. Dethier, for an excellent talk. For people who are here, please post your questions in the chat, or I'm also having a look at the YouTube live stream.
Yeah, I have a question. I just wanna in the meantime, people is posting their questions. So yeah, it was really cool, all this research, Professor Dethier. I just have a question regarding those suspended sediment samples that you use to calibrate your analysis, because I guess that depending on the region, those suspended sediment sampling methods would perhaps change, would be different. Like, how do you leverage that? Like, how do you perhaps make those comparable with each other?
Yeah, it's a great question. I mean, it's something that we think so much about, right? Is trying to make the algorithms that we're using as applicable as possible and as reliable as possible, recognizing that they're fallible for sure, and that they warrant lots of on-the-ground follow-up to really confirm. What we've seen in sort of like looking at the mining areas, there really isn't much measurement from these mining areas themselves, particularly in some parts of the world. But where there is that on the ground measurement, and it really would be kind of like a couple samples here, a couple samples there, we have like good alignment with the measurements from on the ground with our estimates. So we certainly wouldn't want to like put this on an exact level down to the milligram per liter, but I think that we're pretty confident that we're in the right ballpark, certainly order of magnitude, and like our methods would suggest that we're within a factor of 2 for most of our estimates. So imperfect, but absent other measurements, we think it's kind of like the best we've got. And it really does have this benefit of being able to look back in time to the 80s, especially for some of these longer lasting operations. That can be really helpful to have that reference, both for understanding the magnitude of the change, but then also thinking about like rehabilitation and restoration, what the goal might be for setting some of these landscapes on a path towards recovery. I think it's helpful to be able to look back at those reference times as well. Yeah, but again, it's something that we're always trying to do. Actually, this is a perfect time I should plug. I have a NASA funded project right now to have a citizen science sampling campaign. So we're setting up a campaign for people like all of you to go out in the rivers that you operate in and take a really simple sample and send it back to us. And as we develop those, we're hoping to essentially diminish the Northern Hemisphere, or like the North America bias of our sampling, and have a more distributed approach that helps us with calibrating better. Yeah, so if you're interested, if you've got field work far afield, definitely ping me and I'll send you a sampler so that you can just take one and send it back to me. Yeah.
That's awesome. Thank you.
So there is a question in chat by Mamoon. He said, thanks for a nice presentation. Can ecology and economical development go together? And just to add on that, my part is there really a safe way to do a river mining, like with all regulations?
Yeah, I mean, hard to say, right? Like, I think it just depends on what the environmental impact that you're willing to say is compatible with the ecology is. And I think on some level, the reality is that these mining operations are happening. The people who are doing the mining, like, that's their livelihood. And there are a lot of people who are in that situation. And so it's going to be really hard to sort of like turn the full ship and I think across the world, what we've seen is when people do, when governments impose like outright bans, they're really difficult to enforce. Lots of these places are in frontier lands. There are places where there's not a whole lot of state presence. And even when there's like relatively strong states, it's difficult to enforce the mining bans. So that's why, especially sort of in the short term, it feels as though doing some of these more best practice interventions can preserve a semblance of the ecology and the morphology. And then we can work towards some of the like more sweeping policy interventions later on. But even simple things like not including mercury on site is probably a big benefit to the ecology, or to the extent that you can preserve topsoil, like the upper layer that might have a higher density of like carbon, nutrients, and fine grained sediments. That's really powerful as well. Yeah, but it's a great question. I mean, I certainly don't have like a full answer to that. Yeah.
Yeah, thank you. Also, Shan Tian is asking if in the future research, does your team consider to improve the suspended sediment concentration inversion algorithm? For example, incorporating machine learning or deep learning. What are the biggest challenges in this SSC inversion? And yeah, thanks in advance.
Yeah, so great question. We certainly machine learning is part of the, like that's incorporated in our approach so far. Deep learning, like I work with several computer scientists and computer vision researchers at Wake Forest, so we're working on some of that as well. The biggest challenges, honestly, are in the sparseness of the calibration data sets. So just like not having enough samples that are from like a diversity of different rivers. And what we really see is that it doesn't really matter the algorithm approach. Like some of our kind of like little tricks of the trade help us get towards improved estimates, but there's kind of like an upper limit that we hit that's due to just variations in the amount of sand that are in the river, transported by the river, or variations in mineralogy that are difficult to capture on sort of like a general basis. And that's why, like, again, I just don't see this as being like a full replacement for in situ sampling. Like if you really want to know the number, it's helpful to have a little bit of both. What's really nice is that this can extend our estimates in time and space in a way that it's like really difficult and expensive to do with in situ sampling. So yeah, we're definitely working on improving these algorithms, and like send me samples or sample information. I love to incorporate new stuff into the model. But when you really want to know at a certain spot, it's like, yeah, having samples from that spot, even a few, can really help like tune these algorithms so that they're site specific. And I think that really like works the best. So even if you have like 5 measurements from 1 year, that allows you to look back through 30 or 40 years of record and do a lot better, be a lot more confident in your estimates.
Thank you. Miles Reed is asking, have you looked into combination the SSC predictor with multi-temporal LiDAR?
Yeah, also a great question. Yeah, I mean, definitely that's the hope, is to look at some of these areas and try to estimate fluxes out and erosion volumes from looking at like the difference in excavation. What's challenging is the LiDAR data can't capture what's underneath like the water surface for the most part. And so in these areas where like the mining landscape is mostly mining pits that are filled with water to the level of the water table, there's a bunch just missing from a difference of DEM that you might do from LiDAR that makes it difficult to really quantify, okay, how much have we lost here from a LiDAR perspective. So again, like we're doing our best with these types of estimates, but yeah, it's one of those things that will inevitably also be a bit imperfect. Yeah, great question.
Thank you. There is other question from Desiree Tullius. Is there any way to adapt the mining practices to reduce their impact? Also, they're finding that gravel mining pits in the PNW, which were constructed off-channel to minimize their impact on the river, have become hotspots of cyanobacteria blooms and invasive predators. They are still connected to the river at higher flows, so even those low impact practices still have very long-term impacts.
Yeah, I mean, again, it's I think in some places it's probably like verges on an intractable challenge. And this is why, like, long term, probably some of the solution would be towards like just doing less mining. But just in the short term, it's difficult. And particularly as like we're trying to increase mining operations for like an energy transition that requires lots of critical minerals that might be mined in circumstances like similar to the ones that I've shown today. I think like, yeah, it's important to get it right. I would love to chat a little bit more about what you're finding there in the PNW. I assume that's Pacific Northwest, because yeah, that's really important to try to consider all these different eventualities. And certainly this is the value of having scientists working on this problem, right? Is that a solution that might seem like, oh, that's gonna be the fix. If we identify it as not a fix or creating more problems than it solves, then that's really important for policymakers to know, because then we wouldn't elect to go that route. Yeah, thanks for the question, and definitely would love to chat more.
Thank you. Leo is asking, do you think it's a good idea to measure suspended sediment using spectro-cameras instead of taking samples? It will help to cover more areas and measure the peaks of the tributaries.
Yeah, I think it's a great idea for sure, especially in the places where like the rivers are smaller, because you can get a camera that takes a picture more frequently, where like, especially for these smaller, flashier rivers, if you don't take a picture like throughout like a flood event, for example, you're going to be missing a lot. It's why really like these satellite approaches are best for the larger rivers. They don't vary as much like on a day-to-day basis. So I think absolutely adapting these sort of remote methods to more local methods is a great idea. I think the challenge is just calibrating, but especially if you're looking at like one river system, using a camera might be enough. Like even an RGB camera with like a decent calibration, you might get enough information to make a calibration without having like an additional like near infrared filter, that sort of thing. If you could get a camera that did near infrared as well, that probably would be even better. Having 4 bands is better than 3 for sure. So yeah, good question. Something that we think about, but it's just hard to have time to do everything. So yeah.
Yeah, thank you very much. And we are almost there. We just have 2 more questions to ask, so please be with us. Susan Anderson asked if you have done anything on downstream fate of the suspended sediment, like footprint deposition or offshore deposition.
Yeah, thanks for the question. Thanks for sticking around, Suzanne. Yeah, definitely. So I didn't show this, but in general, the propagation downstream is like quite extensive. So the sediment flows that we can see, sort of like the plume or the effect, it extends downstream in some cases as much as like 500 or 800 or 900 kilometers from the mining sites themselves. So absent that sort of like access to floodplains, it doesn't really seem as though there's not enough deposition to attenuate the signal, basically. So certainly I'm sure there's some, but then that deposition is probably also, picked up by other flows and transported downstream as well. What's really interesting here also is that because this is this truly anthropogenic sediment signal, it doesn't have some of the like floodplain access signatures that you might expect from like a big flood in a place where like floods are what move most of the sediment. So if the river's not flooding, then it's not accessing the floodplain. And so as a result, you're not depositing sediment on the floodplain. And we really haven't seen much in the way of like crevasse plays and that sort of thing that you might expect from having lots of overbank deposition. But there's definitely seems to be some signal of deposition in the channel because we see these like coarser deposits that then get reworked. And then also there seems to be some evidence of avulsion that I feel like there's it's hard to figure out a different explanation that's not some in-channel deposition. But yeah, again, like this is the follow-up because lots of these fine sediments are associated with, contaminant transport. And if those contaminants are then being cast up on the floodplain where people are doing agriculture, that's another vector for, toxins into the environment. So yeah, thanks.
Okay, so the last question is from Take Shetri, asking, have you done anything related to change in river water level, discharge, and flood impact due to mining activities?
I have not. I know in Madre de Dios in now 2 years ago, I don't know, I'm getting my years scrambled, but recently in the last couple of years, there was really big flooding. Not like there was a lot of rain, so it was flooding from major rain events in the wet season. There was some sort of like anecdotal report of that being accentuated by the mining activities through rerouting of the water and there not being as much space for the water to go. But I think this is certainly an area that warrants more follow-up. I just haven't done it.
All right, yeah, that's the end of this seminar. So thank you very much, Dr. Dethier, and for all the people that joined today. Thanks especially for sharing aspects of your research with us. And yeah, we look forward to future research outputs and to continue learning about anthropogenic effects on rivers from you. And yes, we'll definitely try to collaborate. So thanks again to all those who joined today. And Shashank?
Yeah, thanks everyone for joining us today, and we'll have more interesting talks like this coming up. So stay tuned.
Yes, thank you very much, Evan.
Thank you. Thanks, everyone.